All right. Good morning. Actually, good afternoon. So, welcome to EECS 120A. This is my first time teaching an online class, and usually in real life, my name is Hong Wei Zhen. But I feel like since this is an online class, I should create a special feature for it. So I just call myself Professor Usagi, and for every online session, you can choose to call me Professor Usagi or whatever you feel comfortable. So, but so the reason why we are having a class like this is because we are now uh, isolated. So, um, um, so, so we cannot meet physically. So right now, what I really wanted to do is that I encourage you guys to speak up and tell me about who you are and what you're feeling about staying at home.
Design. So what is logic design? So the basic idea of logic design, if you go to the Britannica, which is a very famous encyclopedia, this is the definition. So it basically tells you the basic organization of the circuitry of a digital computer. And all digital computers are based on a two-value logic system, either one or zero, on or off, yes or no. And computers perform calculations using components called logic gates, which are made up of integrated circuits that receive an input signal, process it, and change it into an output signal. The components of the gates pass or block a clock pulse as it travels through them. And the output bits of the gates control other gates or output the result. And there are three basic kinds of logic gates called AND or NOT. By connecting logic gates together, a device can be constructed that can perform basic arithmetic functions. So that's logic design. And the most important thing why we are talking about this, as you can tell from the slides, is that a digital computer is used everywhere. And the digital computer is based on the logic system. So that's why we have to figure out how to do this being an engineer in computers, no matter you're a computer scientist or you are an electrical engineer. So what's digital computer? So if you talk about computer and if you check the definition on computer from the dictionary, what it tells you is that it's a programmable and usually electronic device that can store, retrieve, and process data. And it's widely used. So when we talk about digital computers, these are probably the things that come up in your mind is that you would have like on the top left corner, we have a desktop computer, we have server computer, we have game consoles, we have laptop, we have iPhones, we have Tesla, we have another game console. So everything here is basically are basically digital computers. So and to this, and if you tear them down, you will figure out those digital computers, they have a lot of commonality in a way that they all have a circuit board, they all have a few processors, and they all have a few slots that you can put another circuit board, for example, your DRAM, and whatever accelerator card that you have to assist the operation of the computer. So that's the basic idea of digital computers. And every computer, they have these components, and it becomes really important being a computer scientist, computer engineer or electrical engineer to figure out how to design and how to use these components. So right now, when we talk about computers, those are the computers that we have in your mind. So most of the computers you have in mind, they are digital computers. But why I keep emphasizing those digital computers is because there are also computers that are not digital. So this is a computer used in World War II that tried to control the launch of the missiles or those rockets, and you can see like this control is basically this is still a computer because you still give it some kind of instruction and it will automatically does the job that you assign to it. However, this really big computer, it's actually not digital computer. it's an analog computer in a way that it receives analog signals. And and there are more analog computer at that moment. So like in 1947, there's Fermic. So Fermic is used by Fermi, and it's used in a lot of research. And this is uh, Miniac. So it's another analog computer. So there are a lot of analog computers. So, but right now when we talk about computers, we only think of digital computers. So why digital computers are more popular now? So this is the question that I right now want to ask every of you. All right, we are closing the poll in 10 seconds. 5, 4, 3, 2, 1. Okay, so right now, according to my screen, I found that 11% of you think it's A, and 11% of you think it's B, 20% of you think it's C, 17% of you think it's D, and 41% of you think it's E. So that's what do you think right now? So it looks like most popular answers is E. So let me let me let me let me let me so let me so let me so it's a good time for us to figure out why it is that now. So if you have any idea why you want to defend for the answer you chose, please raise your hand. I will pick one of you to speak up.
Yeah, so I was thinking about it, and I mostly agree with the statements, although depending on like kind of how you look at it, the digital
Mm-hmm.
computers can express more values than analog computers.
Mm-hmm.
This one actually I think depends on context because
Okay.
in early digital computers with their lower bit counts were actually considered less efficient with their stepping than an
Mm-hmm.
analog computer would have been.
Mm-hmm.
I think it was only at sufficient memory sizes that we could express enough numbers for it to mean something.
Okay, so
Um,
so here's my explanation to it. So this is analog circuit, right?
right.
And so let me give you a point, right? In this circuit, say like this point. What's the value of it? What do you
Mm,
think the value of this per circuit? This point it is.
if I'd have to garner, I guess it'd be about 0.42,
0.4 something, right? And
0.42, 0.43.
yeah, something like that, right? So the interesting thing about like analog is that if you keep zooming, because the signal is contiguous, right? Continuous,
Right.
right? So you can zoom in unlimited, very unlimitedly, right? So you can have
Right.
infinite possible values within your analog signal, depending on how detailed the resolution you want to be,
Right.
right?
Yeah.
However, if you are using a digital signal, right? First of all, if I want to design a value for a certain point, I have to sample this whole signal within a given sampling cycle, right? And
Hmm.
then I would use some kind of sense amplifier to figure out like what's the value inside there. And
Yeah.
depending on the level of the voltage value, sometimes it could be higher, it could be lower. That's how we decide if it's 0 or 1, right?
So that's how we get
Right, and you
delta
can
sigma
definitely get more
signaling.
values, but it also needs more sense amplifier. And if you look at the blue curve that I draw here, right, it's mostly like this,
Yeah.
and it can never be as smooth as this ones, right? This analog signals, right? So
Hmm.
that's the difference between analog and digital signals. So in this way, do you think analog signals or digital signals can express more values?
I think, yeah, in this context, you would imagine analog signals to express more data.
Okay, so that's the idea, right? So
Mhm.
any other thoughts about the slides? All right. So if not, then thanks, Michael. And I have Chris here. Hello, Chris.
Yeah, hi. Can I please use the bathroom?
What?
Can I please go to the toilet?
Okay, sure, definitely.
I
All
could
right.
shit. Yeah.
All right. All right. So I guess most of you think it's E, and the only thing, but Michael just mentioned a pretty good point that number two, well, it sounds sketchy, and through our explanation, I think you guys must should know that it's not really like it is, right? So so the second thing we know is not correct, but how about others? So let's look at the first one. So when we talk about the first one, the cost of building circuits, we have to go back to this guy, and you must heard about this all the time, is Moore's law. So Moore's law has been the most important driver for historic CPU performance gains, and it's coming from a paper in 1965, cramming more components onto integrated circuits. And this is a very long paper, and if we want to see what's going on there, I can give you a summary of this, and now you can claim to people that you really read this paper. So first of all, what's in the paper is that, well, integrated circuits are increasingly more popular. And they are well established, and they are reliable, and they are small. And finally, they are easy to manufacture and getting smaller and smaller. And heat is not an issue at this moment. And designing ICs can be easy. And they are widely applicable. And so what Moore's law really tells you is that with those circuit with those digital circuits with this kind of transistors, they will become really easy to design and really cheap to design. So so that's why the first statement about the cost of building digital circuits becomes correct. And the thing is that the cost is even lower and lower because within the same silicon die area, we can increase the number of transistors. Uh, we can double the number of transistors every 12 to 24 months. So so this is the Moore's law. And then if you look at uh, uh, the, the, the trend of Moore's law, so this the horizontal axis is the year, and the vertical axis is the number of transistors that we can put within the same area. And you will find out it's basically like a straight curve, meaning that Moore's law is the most important driver for historic CPU performance gains. And some people claiming that Moore's law is dead, but that's actually not quite true. Because if you keep looking at the graph, and even though I should expand the graph to 2020, you will figure out that the transistor count still keep increasing. However, it's more about the power consumption issue that hinders us from putting more transistors within the same area. So the first one, the cost of building systems with the same functionality is lower by using digital computers. That's correct. In the second part, we talk about analog signals and digital signals. And as you can, as I just explained, because for digital signals, it's really depending on how you can quantize your analog signal. So they cannot, the resolution of your quantizer. So they cannot express as those unlimited numbers that analog computers um, can express. So another thing, right? If you look at this graph, you will figure out that the range of zeros and ones within a signal is relatively large. However, for analog signals, if you miss this point, you just miss it. Right? If this point is changing a little bit, then the whole thing becomes different. However, even though in digital circuit, if my point for some reason my signal decays and drop to this this line, I still can tell it's a zero, right? So if you look at that, you will learn one thing is that, well, the digital signals, they are less fragile to noise and defective low quality components. All right, so let's talk about the digital signal, the storage of digital signal. So to store analog data, so these are the stuff we used. So recently, so I don't know how many of you know this guy. Well, it's an audio tape, right? So there's a very interesting Twitter that I saw a few weeks ago. Is that, well, if you know what's the usage of this pencil and the audio tape, and you have a trouble and you might be at risk, you should self-isolate it. Although recently we learned a lot of things telling us that even young people can get coronavirus, right? So everybody should stay at home at this moment. All right, and there are a lot of different analog devices. For example, like this is a videotape, and this is the rewinder of the videotape. And it's probably not part of your memory, but it's definitely part of my memory. So so these are the example storage of analog data. And in the past, in some like cluster computer centers, we do have the tapes to store your storage data as well. So those are the data storage that we have. So here I can give you a clip of the YouTube. They compare the difference of CD, which is a digital storage, and the tape storage that you will hear later. All right, I think we should have enough. Although I don't, well, you can tell a slight difference, like you know, the smoothness of the video, but the audio quality. However, I do believe the guy who recorded this video, he maintained his audio tape very well. So, but most of the time, right, digital data, they are easier to store because when the tape is aging, your signal might fall into a place that's far away from your original quality. So most of you chose D. However, for this question, the answer is actually E. The answer is actually D. All right now. So right now, if you have some question, I will give you the last chance to ask about this question. So Michael, what do you feel?
We didn't hear any of the video.
Oh, you didn't hear any of the video. All right,
No.
but you have the link, so you can go there now.
Okay.
Yeah.
But
Okay.
yes,
Thanks for
it didn't
letting
play.
me know. Yeah, it's kind of weird. All right. So the very basic numbering system that comes from the human nature is 10-based number systems. So because a majority of human beings, we have 2 hands, we have 5 fingers on each of the hand, right? So that's why 10-based number system is popular since thousands of years ago. So for example, in Egypt, they have this number system. So you can see like this means a 1. And then if you want to represent 10, so this is 10. And this is 100, and this is 1,000. This is 10,000, and this is 100,000, and this is 1,000,000. So if you see a number like this, right, then it means 2020. So that's the Egypt number system. And it's pretty close to the 10-based number system we have. And many other cultures also have the 10-based number system. So that's why you see a lot of symbols in many different countries. They all have their numbers from 0 to 9 instead of having something more than that. So, however, if you look at the digital signals, we can only have zeros and ones. We can only have zeros and ones. So in this way, how are we going to express our numbers, our input values? Then it turns out that we need binary number systems. So for so here's the history of binary numbers. So the modern binary number system was studied in Europe in the 16th and the 17th centuries by Thomas Harrod, Juan Camarel, and and Leibniz. If you ever take different differential equations, you must know him, right? So however, a lot of cultures claim that they have the binary number system concept. So for example, Egypt, China, and India. So the binary system is actually not that so obsolete in the human nature. It's just because we didn't catch it in the past. However, when we have the digital design, when we have the idea of digital, then we figure out that there is a value for that. So the basic idea of a number system is that each position in a number system represents a quantity, and symbol in position means how many of that quantity. So for example, in decimal, it's a base 10 system. So we have 10 symbols from 0 to 9, and more than 9, we will have to go to the next position. And each position is incremented by power of 10. And for binary, we only have 2 symbols. And if it's more than 1, we go to the next position. And each position is incremented by power of 2. So, so if I have a number of 3, 2, 1, and you know, like the last, the right hand, the rightmost, it represents 10 to the 0, so it's a 1. And the 2 here represent 10 to the 1, is the second least position. And then the most position here is 10 to the 2. So the whole number add up to 321. And however, if you use a base 2 system, if I give you a number like 1001, then it's similar. The rightmost is 2 to the 0, then 2 to the 1, 2 to the 2, 2 to the 3. If you add up all of them together, it will become 9. So that's a basic idea of a number system. So, so right now is again the time we are going to give you a poll. So recently in Urban Dictionary, I learned a new term called covidient. So there's a person who have a lot of goods and denying them from their neighbors. So like I have exactly this kind of experience is that I went to the grocery store several times in 3 weeks. Well, not every day, but occasionally within these 3 weeks because we want to reduce the chances that we go out. And it turns out that I cannot find any egg in the grocery store. Right. So and finally, I found a farm to give me the eggs I need. So right now, I'm asking you this question, and how many eggs do I have now? Okay. Some of you already got it, right? So if we cannot count with all his fingers, it's more than 10, right? But the thing is that the binary needs 5 fingers, five digits. So this is 5. So what really is that we are having a number that is above this but below this. And for this, if you convert it to digital, the decimal is actually 16. And for this is actually 31. So the x is between 16 and 31. So the only valid answer is 24 here. So is that clear to you now?
Yes, so technically you would still need 5 fingers to count all of them, is that correct?
Right, and the thing is that if you have both fingers, both fingers from both hands, you can have 10 digits, and that allow you to count up to 10 to the 23. Right, so your hands can be actually more powerful than you can imagine.
So basically, in the case of Sean Rawless, he can't be counting with 5 fingers because he's a pussy-ass bitch because I'm going to cut off one of his fingers.
Yes. All right. All right. So Fernando, do you have anything you want to share? Yes. Questions?
I think you passed by me the first time and you didn't unmute me that time. That's why I didn't speak. But
okay.
Yeah, I picked E as well, but now that I heard all these explanations, I totally understand why it's D.
Mm-hmm.
But I just want to say that it was, the whole question was kind of ambiguous and didn't really make sense to me because I kind of assumed from the first sentence that he was referring to 10 fingers. It could have been 10 or anything. I don't know. Like if the sentences were kind of like organized a little differently, it probably would have made more sense to me, but I get it now. So
okay, thanks for the comment. All right. So so right now I'm going to put all your hands down, and if you still have questions to this question, raise your hand right now. Okay, Sean, do you still have questions? Hello?
No, I understand the question now. It's just the academic policy and the guidelines still adhere to this, and it's also recorded on YouTube. So I'd just be more careful about what you say.
Okay.
Thank you for keeping the lecture going.
Okay, thanks. All right, so EIYE, hi, anything to share?
Yeah, man, the last guy's a pussy, that's all, man.
All right, so Xiangying, do you have anything to share?
Oh yeah, so understand, so technically C would be a valid answer as well, right? Because you don't only have 10 fingers, so you can't express 12.
Yeah, well, so so the wording here is, I probably need to polish this better. So we exactly need 5. Exactly.
Oh, exactly. Okay.
Okay.
Okay, that makes sense. Yeah.
Okay. All right. So Sean, do you still have questions?
No further questions.
Okay. Thank you. All right. So Nick, do you have questions? Hello?
Yeah, I had a question about like the eggs. I didn't understand how So if it's like 10 hands, is it,
Okay, so the thing is that if you use all your fingers, you can have 10, right? But right now, if we only exactly need 5 fingers, if we use a binary number system, then you can use this 5-digit to express the number from binary 1 plus 4 zeros to all ones, right? And this thing is actually equivalent to 16, and this thing is actually equivalent to 31. If we want to convert a number from decimal to binary, this is what we are going to do, right? So if you don't remember, let me go through this example real quick. So first of all, you have to divide a number, given number by 2, and if the remainder is 1, then keep it here, and then divide it by 2 and keep the remainder like this, and then until you reach 1. So this is how you operate it. And then what's the number? What's the binary representation of 3, 2, 1? And it turns out that it goes this way, from the bottom to the top. So then 0B 1 0 1 0 0 0 0 0 1. That's the resulting binary number for your decimal number 3, 2, 1. Okay, so with binary number, the benefit is that it becomes really easy for you to convert from any base that is order of magnitude of 2. So for example, if I have an octal system, which is a base of 8, then what you really need to do is to merge 3 digits within your binary representation into 1. Then that turns out to be 501. And if it's a base of 16, then you can basically have 4 digits combining as a single digit in the from the binary and make it a hex number. So it becomes 141 in this case. And if you are familiar with the C programming language, if you add a 0 in front of a number, it represents is octal. And if it's 0x, then it's hex decimal. And if it's 0b, like this, and it's a binary number. Okay, so in the rest of the lecture, I will keep using this convention to express a number in terms of what kind of number systems they are. So so right now I have a so this is the binary number system. So so I'm going to give a pause here. Well, so far we have learned logic design in a way that is basically tell you about how to design a digital computer, and the digital computer is based on a 2-value logic system, is 0 or 1s, and computer from, however, how about the rest stuff like logic gates, integrated circuits, input signal, how to process it, how to change it, how to output it, and what are those logic gates like and or not. So these are the stuff that we will talk throughout the class. And then beyond this, these are also the topics that we will learn. So we will learn combinational logic. We will tell you about what is logic, what are logic gates, what is Boolean algebra, what is CAN map. We will tell you about finite state machine. We will have clock. We will tell you flip-flops, and we will introduce a few data path components that are common in IC design. And we will talk about RTL, the Verilog. So a few of you are thinking about why we are learning this logic design. So the reason why why we are learning about this logic design is just because it's really important, right? So for E major, you probably know why, but for computer science major, when we talk about what do we care? We care about writing a program. So this is what you care. You care about algorithms, you care about data structures, you care about software engineering, you care about programming languages, you care about user interface. But regarding computer hardware, I know this is what Phil, right? So you probably don't care what a computer, what computer hardware is. However, if you look at this program, right? This is the LeetCode, which is probably one of the most famous website when you guys are preparing for job interviews. And for this question, it calls single number given a non-empty array of integers. Every element it appears twice except for one. Please find out the single one, right? So this is a programming question, right? And if you look at the solution, and if you think about like, okay, linear runtime hash table is probably the one you are thinking, but if we cannot use extra memory, then hash table is definitely not the idea that we are pursuing. And turns out if you go to LeetCode, this is the answer they announce. They tell you that you have to use this guy. You have to use bit exclusive OR. So if you never know how numbers are represented in computers, how the effect of an exclusive OR gate is, you will never figure out what's going on here. So this is why you need to learn, because you need a concept of logic design to have it. So, and the other thing is, even though you think, well, I seldom have to deal with this bitwise operations, then how about, and I'm just going to be working in a software company. However, if you look at that, the microprocessor performance does not scale well now. Like in the past, before 21st centuries, we can double the performance of your processor speed every 18 months. However, right now it's getting slower and slower. So that's why every time when you buy a new computer, you feel like the performance gain is incremental. But in the meantime, because we have a lot of demand in computation, so we have to accommodate this demand. So it turns out many of the software company, like Microsoft, they start to build their own hardware. Like this is an FPGA board held by Doug Berger, and he is actually the leader of the Microsoft research and the infrastructure team for Microsoft. So even you are doing AI, right now you have to know hardware. And the same thing for Google. They built their own tensor processing unit, and they have their third version right now. So they hire a lot of EE people, including a lot of my colleagues in Intel, to design a tensor processing unit to accommodate the demand of running applications. So right now, even a software programmer, even though you are working for a software company, you might be asked to use or design this accelerators. Hi, Ding, do you have any questions? Hello, do you have any question? Okay, if you don't have question, please put your hand down. All right, so okay, Nicholas, do you have any question?
Yeah, I was actually just curious what a TPU is.
Okay, so you guys heard about TensorFlow, right? So the tensor processing unit is an AI accelerator that focus on accelerating important key operations in TensorFlow. So for example, when you train a deep learning model, you use a lot of matrix operations, and tensor processing unit is some kind of matrix operation accelerators designed for this purpose. Is that good?
Yeah, that makes sense. Thank you.
Okay. Okay, so Fernando, do you have any question?
Out of curiosity, I think you just mentioned something about us knowing what a tensor is. I just came from CS61.
Mm-hmm.
You're kind of aware that a lot of us don't know these kind of stuff, right? I just want to make sure. I'm not sure the backgrounds of the other people. I'm a junior BE major. I haven't taken a lot of
Yeah, so I'm not going to tell you exactly about what a tensor processing unit is. I just want to let you know, well, right now it's in use and it's important. And if you don't know circuit design, then you are not going to know it.
Okay.
Okay. All right. Fang Zhongliu, Li.
Hi, Professor. Can you
Yes.
hear me?
Yes.
Okay, great. Could we go over that LeetCode question that you showed us?
Okay,
because I
you
didn't
are
really
interested
understand the
about the
loop.
LeetCode question?
Yeah, no, the one that you just showed us about the
This one?
using binary to solve this problem without using extra memory.
Yeah.
I didn't really understand the solution.
Yeah, I mean, if I want to expand it, well, so basically is that you have an exclusive OR in here, right? So when you have an exclusive OR, if it's something the same, and it turns out they will cancel the things to be zeros. So you will know this you will know more after you learn digital design. All right.
Okay. All right.
All right. So hopefully that did give you guys a pretty good motivation to move forward. So right now, what I'm going to do is that, well, so like Google, and even Facebook, they are designing their own hardware, and Amazon as well. So it's really important. So in addition, every computer right now is becoming this way. Is that in addition to the processor, storage, memory, data we also have FPGA, GPU, TPUs, those kind of stuffs are now in your computer. And being a software computer engineer, you have to interact or even have to design this hardware accelerator as in software. So that's why this class becomes really important. So right now, I'm going to talk about the learning experience of this class. So this class is basically, we are going to do 4 things: read, think, learn, and practice. So for the read, we have a textbook, which is actually a Zai book. I should update here. It's actually a Zai book. You guys probably already received the link from the Piazza. And we will have polls like I have go through with you in this lecture to lecture practice to bring out misconceptions. And then through those lectures, through those questions, you will learn. And finally, when you learn this concept, it's really important for us to practice. So we will have assignments help review what you have learned during the lectures, and we will practice learn concept into lab experiences. So this is a textbook. It's digital design by Zai Books, and it's written by the CS professor at UCR, Professor Frank Bahid, and he gave us for free. So thanks to him for doing this for us. Woohoo! All right, and this is a big book. It has a lot of valuable materials inside. However, I'm not going to cover everything in class, and it's your responsibility for all the assigned text and complete assigned chapters on Zai books. And also for your reading quiz, we will have reading quiz to make sure that you went through the book at least in some degree. And you will have you won't have a time limitation until the deadline. And however, we will drop a few lowest ones, so there is no makeup reading quizzes if you miss the deadline. So this is how you subscribe to textbook. And please sign in and create an account if you haven't done so. And here's the code, and please subscribe. And during the lecture, I will bring in activities to engage you in exploring your understanding of the material. And I will have pop-up questions like what we did today. And each individual, you will think, and we will have a whole classroom discussion. There are some fluctuation today, but hopefully in the next time, we will do a better job. And for the learning part, we will learn after discussion explanation on each concept. And we will have discussion forums on Piazza. And the lecture experience is mostly like today. I will lecture and I will poll. And after the poll, that's the time each of you can discuss, can share your thoughts about the question. And we will repeat the same process again and again. We will have 6 assignments, and you will have to complete these assignments on Zai book. And it's using we also have 6 labs using Verilog and simulation tool to verify and evaluate your design. Logistics. So this class, we have a lot of resources. The lecture time is on Zoom, and we will have scheduled slides on course webpage. We will have discussion on Piazza. We will have reading quizzes, lab submissions on iLearn. We do YouTube live streaming and lecture videos, and we will have assignments and reading on Zai books. So this is the tentative schedule. You can also find the same on the website. And for the schedule, you can see, well, after today, almost every, before every lecture, we have a few things due. So make sure that you go to our website and check out the deadline carefully. All right, so a few of you have questions. So right now, first of all, I will put all your hands down, and if you have questions, raise your hand. I will give you 3 minutes, and I will, if we cannot, and I'll have to go through, right? Okay, so Michael, what do you think?
Office hours, when do you have them?
Okay, I haven't done it. I will go through there. All right, and all right, so this is the schedule we have for now, and this is the grading. We have reading quizzes on iLearn. 2 attempts each quiz. Take the advantage. We'll drop the lowest and check the website iLearn for the due date. Join the class if you participate, and we will give you 2% of credits. We have 6 assignments throughout the quarter. We'll drop the lowest. We have 6 left. We'll drop the lowest. We will have midterm and cumulative final. So that's the grading policy. And this is me, and most of the time, if in real life, I look like this, but in this class, I pretend myself to be this guy. And I got my degree in computer science in UC San Diego, and before I joined UC Riverside, I was also an assistant professor at NC State University. And here's a link for my Zoom office hour. You can also find a link in iLearn now. And these are our teaching assistants, Yibo and Lu Ting, and they will each lead lab sessions on Wednesday, office hour on Wednesday. Well, they will lead lab sessions on Wednesday, Friday, and office hour on Wednesday, Monday, and plus my office hours on Tuesday, Friday. So every Monday through Friday, we have somebody to help you out. And teaching assistants, they are the main leaders of the lab sessions. So we will release videos on Tuesdays, which we already have one available after this lecture. And please attend to a registered session virtually through Zoom so that we can have some kind of lab sessions. And before you go to the sessions, make sure that you watch those videos online. And they are technically just group office hours. And you can jump in whenever you have a question. You don't have to be online in a Zoom for 3 hours if you don't have any question to save everybody's time. And on iLearn, we have a lot of resources like course webpage, Zoom, YouTube channel, textbook, Piazza, office hours. You can find out those information. They are all on iLearn. And we have, if you want to figure out what your grades is, there is a tool section in iLearn. You can go to My Grades to figure out your grades. And you can see your grades on iLearn. We have a 1 week regrading policy. If you figure out there are something wrong in your grading 1 week after the grade is announced. However, if you pass that 1 week deadline, we will not do any regrading for you. And don't cheat. And this is the most important thing. So these are all the classes that have been taught before, and I hope by the end of this quarter, I would take a photo and put you guys up here through Zoom. Other than that, the most important thing that I want to announce is that Lab 1 is online, and please attend your assigned lecture, and Reading Quiz 1 is also online. Please go through those informations. And thank you.